postulate is something in math that is kind of so basic that we can't prove it's true, we just assume it to be true. So it's a basic assumption, something we assume to be true, and it's not proven. Okay, an example would be, all right, let's say we have a line segment from here to here. Let's say from here to here is 3 long, and from here to here is 6 long. How long is the entire line segment from there to there? 9. Okay, that's actually a postulate. So if it's 3 from here, 6 from here, altogether that's 9 long. That's called the segment addition postulate. Okay, just kind of a basic idea that we assume to be true. Okay, this is just an example, segment addition postulate. That this part of the segment plus this part of the segment equals the length of the entire segment. Anyway, so that's just to give you an idea of what might a postulate look like. Something that's kind of basic that we assume to be true. To build kind of a logic, an understanding of what works and what doesn't work, you have to start with basic assumptions. Not just in math, but in anything. How we see the world, our worldview is affected by our basic assumptions about life. If you're an atheist, you might think that we're just an accident and nothing we do here really matters, and that's going to affect you a lot. You're assuming some things are true based on your idea that God doesn't exist. That affects you a lot. Or if we are theists, we believe in God. So that's going to affect us a lot. So anyway, that's kind of your starting point. And in math, they're called postulates. These are kind of our building blocks to understand how math works. But you got to start somewhere. You got to start with assuming something is true, and that's called postulates. Okay. Then after postulates comes theorems. Actually, you guys should all know the name of one very popular theorem. Pythagorean theorem, yeah. Theorems are things that can be proven to be true. They're not necessarily complicated. They can be complicated. But they are proven based on postulates, definitions, and previously proven theorems. Okay, the Pythagorean theorem, we're going to later on down quite a ways down the road actually, we will be going over Pythagorean theorem quite a bit. That was the right triangle thing where if the legs are A and B and the side is C, A squared plus B squared equals C squared. Okay, now you wouldn't know that just by looking at it, right? That's something you wouldn't say, well, that squared and that squared equals that squared. That's something that's kind of, you wouldn't guess. But people have proven it's true. Actually, they've proved it a few different ways. Using postulates, basically, and some definitions, to figure out that that is going to be the case every time in every right triangle. Somebody figured that out. Anyway, that would be the example of a theorem. Another one, here's a more basic one. And this one's based off of a definition. Midpoint. Guess what? If M is the midpoint of AB, guess what that means? What do you think it means if I say M is the midpoint
It's the middle.
of segment AB? It's the middle? And how could we say that, like, more definitively, like with a better definition, it's that AM equals MB. In other words, the length from A to M would be the length from M to B if M is the midpoint. Does that make sense? If it's right in the middle, these two are the same, right? That would be the definition of a midpoint. Now, notice I mentioned definitions right here. But there's something else we could say. If M is the midpoint, what do you think we know about the length of AM compared to the length of AB? How might the length of AM compared to the length of MB if M is right in the middle? If M is the middle, how might the length of AM compare to the length of AB? Anybody? Maybe you don't know what I mean by compare. Like, how much bigger is this one than this one?
Divided by 2.
It's twice as big, yeah. So that would be a theorem. That would be called the midpoint theorem. That this segment is half of this segment. You could use that you could prove that using the definition of midpoint and some algebra postulates, but that's another example. Okay, anyways, so we got these two major definitions today, postulates and theorems. And we're going to be talking about a lot of those. So all these postulates and theorems, let's see, what page are they on? They're on page 12. So go ahead and flip to 12 if you haven't already. All these postulates have to do with points, lines, and planes, the stuff we talked about yesterday. So some of it will probably make sense. Some of it might be a little fuzzy. Actually, expansion postulate's kind of my least favorite. I wonder if I should say that for last. Yeah, let's go to the line postulate first. Okay, let's see if we can read this, understand what it's trying to say. Now, these are supposed to be kind of basic ideas, like things that we assume are true just because they seem like they have to be true. Okay. Anyway, a line postulate. Any 2 points in space line exactly one line. So if I have 2 random points here, how many lines would contain those 2 points? 1. Okay. Is there any more that could go through those 2 points? No. If you tried to draw another, it'd have to look something like this, right? Like, that's not a line. So, through any 2 points, there's exactly 1 line. Okay, any 2 points you have anywhere, there's 1 line that will connect them. That is called the line postulate. Okay, makes sense, right? Okay, this might be a little more complicated. Any 3 non-collinear. You guys remember collinear from yesterday? Means in the same line. So if any 3 points are not in the same line, they are contained by exactly 1 plane. There's 1 flat surface that will cover those 3 points. Okay?
Maybe 2 planes that cover those exact 3 points?
No. So, let's say these are 2 points and my 3rd point's sticking out here. How many planes could cover those 3 points? Well, there's only 1. It'd have to look kind of like that and touch right there. If you tried to shift a little bit, that would be a different plane, but it wouldn't touch one of the points. So any 3 points are covered by exactly 1 plane. That's why when I said we name a plane, you have to use at least 3 points, because that is the case. So if you try to lift up the plane a little bit, it wouldn't touch and it would be a different plane. Does that make sense?
Mm-hmm.
I was going to say something. I forgot what it was. What was it? Kind of important. Oh, I remember. Unless, if those points are collinear, if they do share the same line, there's actually an infinite number of planes that would cut through those points. So it doesn't work if they're collinear. But if they're not in the same line, if they're non-collinear, there's only one plane that can touch those three. Okay, so this is 2 points contained by one line, 3 non-collinear points contained by one plane. Line postulate, plane postulate. What was the next one? Flat plane postulate. Okay, maybe you guys can finish this sentence. If I have a plane and 2 points are on that plane, then the line that contains those 2 points, guess what we can say about this line? Nobody? So if I have a plane and 2 points are on that plane, then the line that contains those 2 points, what do you think we can say about this line? It's also in the plane, yes. Okay, so if I have a piece of paper and I have 2 points on this piece of paper, then the line that goes through those 2 points is also on the paper, right? 2 points are on a plane, the line containing those 2 points also has to be in the plane. It's called the flat plane postulate because planes and lines are flat, they're both kind of together. That's kind of the idea, I guess. All right, line intersection postulate. Well, actually, before I do this one, no, never mind. We'll do this one next. When 2 lines intersect, where do they intersect at? A point. Right? 2 lines intersect at a point. Could they intersect at more than one point? No. Because that would look something like that. That's not lines. So 2 lines intersect at exactly 1 point. Okay, if they do intersect. Now, is it possible for 2 lines not to intersect? Yeah, what would that look like? Parallel lines. Okay, parallel lines are lines that are in the same plane, but they never intersect. Did I mention this yesterday? I can't remember. If 2 lines, now if my arms were lines, are these lines parallel? No. Are they in the same plane?
No.
So these are called skew lines, when they don't touch, but they're not in the same plane. So if they are in the same plane, same flat surface, these are parallel. You guys are probably more used to this idea. But skew means they won't touch either, but they're not in the same plane. So like if this is one of the lines, maybe a skew line would be like this, not touching but going at a different angle. Okay, but if they do intersect, it's going to be 1 point. That's called line intersection postulate. Kind of makes sense. Okay, plane intersection postulate. What, can we get this without reading? When 2 planes intersect, where do they intersect at? Okay, let's imagine, okay, the ceiling is a plane, right? And this wall over here is a plane. And where are those 2 planes intersecting at? Where does the ceiling hit the wall?
Right there.
Yeah, all along this crack right here. And this would be a what?
Line.
A line. So when 2 planes intersect, they intersect at a line. And they called that the plane intersection postulate, exactly 1 line. So 2 lines intersect at a point. It takes me too long to draw intersecting planes. Kind of like, anyway, I'm going to do it. But 2 planes intersect at a line. Is it possible for planes not to intersect? Can planes be parallel? Yeah. The ceiling is parallel to the floor. Those 2 planes would never touch. This wall is parallel to the back wall. Those planes would never touch. And it's possible for a plane and a line to be parallel. Like if there is a line on this plane, it would be parallel to the black wall. They would never touch. Okay. All right. I skipped 1 postulate. We'll go back to the beginning. This one's kind of silly. Okay, let's read it and then we'll talk about it. That's not my favorite. Okay, an expansion postulate, it's also got the hardest name, I think. I'm not gonna make you memorize these names, but like on the test, it might say two lines always intersect at a blank. Okay, and then you'd have to say a point or something like that. You don't necessarily need to know that. Our book called it line intersection postulate. Another book might call it something totally different. There's nothing really special about these names. Anyway, the expansion postulate, a line contains at least 2 points. A plane contains at least 3 points. Space contains at least, I didn't say it right. A plane contains at least 3 non-collinear points. And space, what we live in, contains at least 4 non-coplanar points. That last one seems kind of silly to me because there is only one space that we're aware of. I told the other class, unless it's like, God created multiple universes, kind of like comic books. But as far as we know, there is only one space. So I don't know why they threw that in there. It seems a little silly. But basically what they're saying is, so if you have a line, it could have infinite points on it, but they're saying, that there's at least 2. There's infinite possible points, and a plane has at least 3 non-collinear. They kind of need this to do other stuff, so that's why they said it. So, anyways. Okay, on the right page, in those green boxes, there's 3 theorems that they list. So theorems are things that can be proven to be true. They're not just things you have to assume. They're proven using like other postulates though. So let's see if we can look at this first one. A line and a point not on that line are in exactly one plane. So a line and a point on that line. You might not know this off the top of your head. Maybe if you thought about it for a while, you could see it's true. But if you have a line, let's say this yardstick's our line. Let's say the end of this marker is our point. How many planes would cover this? Well, there'd be like one sheet of paper that would cover all that. So a line and a point not on the line are in exactly one plane. Okay, there's not 2 planes. The planes would have to go like this. It's not really a plane. So there's only one plane that would cover those. Now, we can prove this is true because using the expansion postulate, we know that this has at least a couple points. And now we have 3 non-collinear points, which the plane postulate says are covered by exactly one plane. So we use those 2 postulates to make this theorem. A line and a point not on this line are covered by one plane. Okay, if you don't remember this, that's okay. You can just look it up. But this theorem does not have a name. Lots of theorems don't have names. So if we have to reference the theorem, like say what the theorem is, we're just going to have to write it out. Just kind of copy it down. Okay, the next box, we're almost at the end there. 2 intersecting lines are contained in, so if 2 lines intersect, how many planes will cover those 2 lines? 1. There's only one flat surface these guys can be on. If I picked this up and moved it around, that flat surface would have to move around with it. It's because, okay, we know there's a point of intersection based on the line intersection postulate. Kind of obvious, right? And we also know that every line has at least 2 points. Therefore, 3 non-collinear points that will only be covered by one plane. Okay. So this is covered by one plane. This is covered by one plane. What's the last one? 2 parallel lines are in only one plane. So yeah, 2 parallel lines, because they have some non-collinear points, that would only be one plane that covers that. All right. Okay, yeah, it's kind of weird. Sorry, guys. They're trying to get us ready for theorems. We won't do a lot with theorems, but I do want to introduce you to the idea. Tomorrow it'll be a little more basic, like finding the length of segments and angles and stuff. I think we're doing a little bit of protracted work tomorrow. Some other stuff, but anyways, we're starting on number 4. You guys see that over there? I think I wrote it wrong on Renweb. Okay, number 4, it's kind of like matching, although these answers can be used more than once. It says fill in the blank with plane or planes, line or lines, point, points, or space. Okay, so those are our options. Our answers are pretty much like in the green box, in the green boxes. So number 5, 2 blank are either parallel or they intersect in a line. So 2 what? Well, there's only one thing that can intersect in a line. 2 what intersect in a line? Planes. And 2 planes, they can also be parallel, yes, but 2 planes intersect in a line. So the answer to 5 is planes. Okay, that was the plane intersection postulate. 2 planes intersect in a line. Number 7, I read this briefly. I said it was kind of silly, but 4 non-coplanar points determine what? Yeah, it was the very first postulate that I skipped for a while, but space is the answer, yeah. So that's the one I think silly. To be honest, you're not going to see that ever again. But the rest of the stuff, you'll see it like in chapter 1. Okay. Yeah, number 7 is just kind of repeating the first postulate part of it. So yeah, number 7 is space. Okay, now the next section. So we're supposed to use that picture on the right to help us do numbers 9 through 16. We're going to have to kind of think about this. We're going to answer the question, and then it says state the definition, postulate, or theorem that supports your answer. So we're going to have to say which postulate are we talking about when we answer this question. Okay, number 9, does line AB lie in plane M? Now they didn't draw line AB, but if we did draw line AB, would it be inside plane M? Yes. So for the first part on 9, we're just going to put yes. But then we got to say what postulate says that's true also. Huh? Yes. Okay. It's basically saying A and B are in the plane, so line AB is also in the plane. And that was the flat plane postulate. If you read that again, it says if 2 points are in a plane, then the line containing those 2 points is in the plane. If 2 points are in the plane, in this case that'd be A and B, then the line that contains those 2 points is in the plane. That's basically what we just said. So flat plane postulate. Okay. Number 11. How many planes pass through points A, E, and D? Now they didn't draw it, but they don't necessarily have to draw it. It'd be a mess if they tried to draw everything. But how many planes have to pass through points A, E, and D? 2. No. It's got to cover all points A, E, and D in the picture. Okay, well, what are A, E, and D? They're 3 points. They are 3 non-collinear points, right? So how many non-collinear points, or if 3 non-collinear points are contained by how many planes? 1. Okay, which theorem said that? Or postulate, rather?
Plane postulate.
Yeah, that's just a plane postulate. A, E, and D are just 3 non-collinear points, so there's 1 plane that covers them, And that is stated in the plane postulate. Okay. You guys hot, cold, or okay? You're cold. How about you guys? This vent's open, this one's not, that's why. How about I just point this towards the middle of the room? I'll just point it away from you. And maybe nobody will be home. Oh, not that far. So that kind of blowing right here. I don't want to close them. It will get warm in here if I close it. All right. Let's see. Number 13. How many planes pass through line CD and point E? So how many planes contain a line and a point not on the line? How many planes contain a line and a point not on the line? How many planes would cover this? One. Basically, it's the smart board. This is the smart board's plane. One. Which postulate says a line and a point not on the line are contained by one plane? Oh, no. That was a theorem. Sorry. That was a theorem. Which, okay. Yeah, the theorems don't have any names, but if you look at the top theorem, it's basically what I just said. A line and a point not on the line are contained by one plane.
So do we write that down?
Yeah, since it doesn't have a name, we're going to have to write it. Sorry. So, a line and a point not on the line are contained by exactly one plane. Okay. 15. What is the intersection of lines ED and DB? If you drew lines ED and DB, where would they intersect at? Where do two lines intersect at? Like what kind of thing? Yeah, two lines intersect at a point. Well, both of these lines have D in their title, right? That means both lines contain point D. So point D must be point of intersection if you drew them both. So the first answer is D. Lines ED and DB would intersect at point D. There's another question on this one. Is there more than one point of intersection? Can two lines intersect in more than one spot? No. They only intersect at one point. So, no. So basically, we got a list now. Which postulate says two lines only intersect once, at one point? The postulate is kind of in the sentence I just said. Which postulate says that two lines only intersect at one point?
Line intersection.
Line intersection postulate. Okay. 16 is weird because it's not a postulate, it's a definition. Can you draw any skew lines? This is 16. Can you draw any skew lines using the points in this figure? So, if you were to draw any two lines, is it possible to draw any two lines that are skew? That means they don't intersect and they're also not on the same plane.
Yes.
Okay, well, let's give an example specifically. There's more than one example, but what two lines in that picture, if we drew them, would not intersect, but they would not be in the same plane either? ED and what was the other one? AB. Okay, that would be one example, yes. ED is going to go through the plane. It's going to go from up, down through it. And AB is on the plane. So they're not parallel. But are they ever going to intersect? No. So ED and AB. Are skew. And that would just be by the definition of skew lines. If they don't intersect, they're not on the same plane. But you can just put that, it's fine. An example of two skew lines for number 16. Okay, for 17, I'm not going to do this one. You just have to kind of copy those pictures and draw as many lines as possible between the points. So how many lines could you draw on A? 1. How many lines could you draw on B? How many on 17B? How many lines could be drawn? Yeah, 3. Gotta be bold and say it out loud. Okay, anyways, you're supposed to draw as many lines as you can in the picture A, B, and C. So I'm not going to do that one. 18 I am going to help with because it's harder. Draw a line in a plane illustrating the possible number of points of intersection between the line and the plane. So what are some different ways that a line and a plane could intersect? And then we're supposed to draw, or interact, let's put it that way. How could a line and plane be related to each other? Like, let me see if I can say it another way. We're supposed to draw pictures showing different ways that a line and a plane could intersect in different amounts. Let's see, that's about the best way. What's one example of a way that a line and a plane could intersect? It could have points of intersection. No ideas? Come on now. Good. Half asleep here. Okay. Here's one way. Well, they could intersect at one point if the line just goes through the plane. This is just called the line intersecting the plane. One point of intersection. Okay, what's another way that a plane and a line could interact though? It could go through the plane, what else could happen? It could be on the plane. Now, if it is on the plane, we just draw it like that. How many points of intersection are there? Kind of a trick question. If the line is in the plane or on the plane, how many times does it intersect? Infinite points of intersection. Okay, there's actually one more besides this. You can get intersect the plane, it can be on the plane. You may think of the last one. How else could a line and plane interact? Okay, is it possible that they would never intersect? Never touch at all? Yeah, remember we talked about if there's a line on this wall over here, it would never touch that wall back there. This plane never touches that plane. So it's possible for a plane and a line to never intersect. They would be parallel basically. So 0 intersection points. All right, that's why we did 18, not 17.
So do we have to do 17
Yes, you do need to do 17. All right, 19. These are kind of like true false, but instead of true false, it's always. So that's kind of like true. Never, that's kind of like false, but sometimes means it's sometimes true, sometimes false. Okay, number 19. Let's give this a look. Two intersecting planes determine a unique line. So in other words, they're saying, do two planes always intersect at one line? Yeah, it's always. They always, that's one of our postulates, but yeah, they always do. So, yeah, I'll just say it. Number 19 is always. 20, these are tricky, so we're going to go through them together. Two intersecting lines determine a unique plane. In other words, are two intersecting lines always in a one plane?
Yes.
Yeah, that was one of the theorems. Two intersecting lines always are in one plane. Okay, 21. 2 points are non-collinear. Is it possible for 2 points to be not collinear? No. Through any 2 points, there is one line. That's called the line postulate. So it's not possible for 2 points, any 2 points, anywhere. There's one line between them. So it's never going to be the case where 2 points are non-collinear. Never. Okay, 22. 3 points are non-collinear.
Yes.
Is it possible for 3 points to be non-collinear?
Yes, sometimes.
Yeah. Sometimes they are non-collinear and sometimes they are collinear. So it could be both. So that's sometimes. Just means collinear just means in a line. Sometimes they're non-collinear on a line, sometimes they are collinear in a line. Okay, 23. 3 points are non-coplanar. Is it possible for 3 points not to be in the same plane?
No.
Not possible, because one of our postulates was any 3 points are contained by exactly one plane. Any 3 non-collinear points. If they are collinear points, there's actually infinite planes that go through them, but they're still coplanar. These are coplanar by infinite planes. These are coplanar by one plane. All right, where are we at? 24. 3 intersecting planes. Okay, if 3 planes intersect, it's always going to be, or sometimes, or never, 1 point. This one's a tough one. It's not in one of our postulates either. If 3 planes intersect, it's going to be at exactly 1 point. Can you guys imagine 3 planes intersecting at 1 point? Yeah. So wall, floor, or wall, ceiling, those are 3 planes that intersect at a point. Is it possible 3 planes intersect in a different way besides 1 point?
No.
I should have thought of this in the other class. So all these pieces of paper are like planes, right? And if I fan them out, where are they intersecting out at? Right here at the corner, right? So all these planes, you know, pretend they're coming in at different angles. They all intersect right here along this ridge. So it is possible for them to intersect at more than 1 point. So sometimes. (25) A line determines a unique plane. So if you have a line, it's only in one plane, basically, is what they're saying. Always, never, sometimes. have infinite, it's kind of like that book I just showed you. Lines could have infinite planes going through them.
Always.
So, I forgot how they asked the question. A line is in one unique plane?
No.
No, never. There's infinite, actually. Just the infinite angles you can come in at. Okay. Do those, goodness, that took a little time. Make sure, I didn't leave you a lot to do, probably like 7 or so make sure you do those evens before tomorrow.